So Ptolemy's solution had a very practical function. Given a point in the line of apsides upon which the planet sweeps equal angles at equal times, the orbit can be parametrized in time. Kepler had two problems. First, Tycho's observations, accurate to 2 minutes, did not allow for the 30-minute error that was given by the equant model. Also, his ellipses, with the planet speeding up at perihelion and slowing down in aphelion, begged the question, what is the equivalent to the equant? What is the point about which a planet sweeps equal angles at equal times? Kepler tried to find the ellipse equivalent to the equant. And what he found was Kepler's second law. It turned out that there is no point in the ellipse about which you can say equal angles at equal times. Kepler's quest to answer this question turned out to be equally revolutionary. It's the second law. It demolished the idea of uniform motion. You have to abandon the idea that time is equal to angle. Kepler's first law throws the epicycles out of the window. Kepler's second law throws the equant out of the window. Now, looking for something that could be a measurement of time, Kepler stumbled in a hunch on what this something was. So if the planets are slower when far from the sun and faster when close, Kepler reasoned that the velocity was inversely proportional to the distance. Now, if that is the case, you can multiply both sides by time and write the proportionality as v times r times t is proportional to t. Now, the quantity in the left-hand side, whatever it is linearly proportional to time. It is this something sought in equal something at equal times. But what is its interpretation? Now, the product Vt is the length of arc that is swung by the planet. Now, if the time is infinitesimal, then the arc is infinitesimal. And then you have a triangle of long sides equal to r and small side equal to v dt. The area of this triangle is r times v times dt over 2, which is what is in the left-hand side of the proportionality. So the left-hand side of this proportionality is the area. As the planet orbits the sun, the area it sweeps is proportional to time. And time is the mean anomaly. So the mean anomaly is not given by an angle. Mean anomaly is given by an area. Okay, the mean anomaly is proportional to the area. The question then is how to compute the area. Now, Kepler did not know calculus, so he could not calculate the area by summing the infinite distances. That would be simple if he was Newton, right? He would write the infinitesimal areas and then just integrate all of the infinitesimal areas and find the area of the section of the ellipse where the planet is. So Kepler did not know calculus, but he was an excellent geometer. After he discovered that the orbit was an ellipse, he used the geometry of the ellipse to find out the area. So Kepler's efforts led to Kepler's equation, which relates the mean anomaly and the eccentric anomaly. It says that the mean anomaly is equal to the eccentric anomaly minus the eccentricity times the sine of the eccentric anomaly. So let's prove this. Kepler found this geometrically. Now consider this figure. The main insight is that pH over QH is equal to B over A. You can see that because CQ is equal to A, the semi-major axis, CQ is this, which is equal to the semi-major axis. And this QH is equal to A times sine beta. And we have already shown that pH is equal to A times the square root of 1 minus E squared times sine beta, which is equal to little b times sine beta, because the semi-minor axis is equal to A times the square root of 1 minus E squared. So that proves that pH over QH is equal to B sine beta over A sine beta, cut the signs, is equal to B over A. Now the area of the circle is 4 times the area of the quadrant. And the area of the quadrant is found by integrating the vertical distances y from x equal to 0 to x equal to a. So y circ is equal to qh. If you integrate these distances from 0 to a, you find the area of the quadrant. And the area of the circle is equal to 4 times the area of the quadrant. Now the area of the ellipse, you can find the area of the ellipse by the same method. The area of the ellipse is going to be 4 times the integral from 0 to a, not of y circ, but y ellipse. And because we already know the relationship between the semi-major and the semi-minor axis, we can write that y ellipse is equal to b over a times the y of the circle. So to find the area of the ellipse, you simply have to get the area of the circle and multiply it by b over a. And since the area of the circle is pi a squared, the area of the ellipse is then pi ab. Now, given that the planet sweeps equal area at equal times, a relationship between mean anomaly and area can be established. A planet sweeps equal area at equal times will, within a time t, sweep an area, call it a sector, where big T is the orbital period. The question is then, what is the area of the sector? Because on the right-hand side, you already have the mean anomaly, right? Pi ab times little t gives you a constant times the time, which is the mean anomaly. We can in fact multiply this by 2 and divide by AB to already write it as the mean anomaly. What you have is 2 over AB times the area of the sector is equal to 2 pi over the period times little t, which is omega t, which is the mean anomaly. Now the question is, what is the area of the sector? All right, consider this figure. The area that is swept from perihelion, which is the point X, to the point P, which is where the planet is the area of the sector SPX. So SP and X. We can relate that to the area of the sector of the circle as QX by again using the same relationship that the y of the ellipse is b over a times the y of the circle. You would be integrating again. So the sector area of the ellipse is equal to b over a times the sector area of the circle. And because this is a circle, we can calculate the area of the sector. The area of the sector SQX is equal to the area of the sector CQX minus the area of the triangle SCQ. The circular sector CQX comprises an angle big E of the full 2 pi circle. So its area is pi a squared E over 2 pi, since it's a fraction of the full 2 pi circle. As for the triangle CSQ, its base is CS equal to AE, and its height is QH equal to A times sine E. We thus find the area of the elliptic sector SPX. The area of SQX is pi a squared E over 2 pi minus a squared E sine E over 2, which is equal to a squared E minus a squared over 2, which is equal to a squared over 2 big E minus E sine E. To find the area of the elliptic sector, we multiply it by b over a. So we now equate that to the mean anomaly. And there you have it. The mean anomaly is equal to the eccentric anomaly minus the eccentricity times the sine of the eccentric anomaly. This is known as Kepler's second law, or Kepler's equation. The left-hand side is time, is the mean anomaly. The right-hand side is area.